Good morning, everyone. My name is Syed. Today, me and our group are out to present our final presentation with the title Applying Improved Approximate Nearest Neighbor Search for Text Retrieval. Our thesis under the supervision of both Dr. Hossam Sharara and Dr. Nouri Sakr. So this is the outline for our presentation. Our project is composed of 3 different modules that we're going to discuss today. So some of you might have heard Twitter just open sourced their main algorithm a couple of weeks ago. And if you take a look at the code, you'd find that they use something called SimCluster ANN. This module is responsible for performing similarity search in order to recommend the tweets to users similar to the ones that they interact and like. And if you take a closer look at the code, you would find that they use 2 very famous libraries, ANN libraries, namely Face and HNSW. And it's not only Twitter that uses ANN. Also, YouTube, in a paper that they published in 2016, highlighting how the recommendation engine work, you would find that they combine a watch vector, search vector, and some other filters into a vector embedding. This is very similar to what we're doing in our thesis. And then they pass this vector through a couple of relu activation layer, and finally perform ANN in order to recommend it to user videos similar to the ones that they watch. So I've mentioned the term ANN multiple times, and I want to quickly recap on its meaning. ANN is derived from the K nearest neighbor algorithm, where for a given data point, I want to perform a linear search in order to find the K nearest neighbor to the given data point. So you might be wondering why not just stick to the KNN? Well, as I said, KNN performs linear search, and this becomes impractical when we move to the billion scale. And also the cursive dimensionality hinders us from using any smart data structure to overcome this problem. So what big tech companies opted to do is that they choose to trade off accuracy and memory in favor of a faster search. And each big tech company has their own implementation of the ANN algorithm. For example, Google has Scan, Facebook has Face, and Microsoft has Span or SB tag. So for our problem statement, we're trying to extend and accelerate disk resident ANN algorithms and use them for a contextual text-based search in a document retrieval system. As I said, we chose Microsoft Span or SB tag for our project because it's the state of the art in the billion scale, and it uses both the memory and the disk. But how does it work? Well, when SB tag is presented with a query, it first performs a search in the memory for the graph centroids. Graph centroids are representative for the data clusters in the disk. And after identifying the needed graph centroids, it then fetches the data from the disk into the memory and perform the computation. And now we're going to present our first module, which is a scalable inverted query mapper for approximate nearest neighbor search with my colleague Mina.
Okay. So on the left-hand side, you can see a demo of how SB tag actually performs the search. When a query arrives at the index, it identifies a bunch of centroids from the disk centroids to load them in order to evaluate them against the query. What we did is that we separated the centroid identification stage from the search so that we know beforehand what centroids would we need to fetch so that we minimize IO from the disk, which is a bottleneck in disk resident ANNs. After doing so, we fetch at most each centroid only once, which saved us a lot of IO time and gave us an edge in terms of speed. Here is an overview of our architecture. It looks complex, but I'll break it down in a second. We start by giving a number of queries. Each query has any variable number of dimension. We support variable dimensions. These queries are then divided among n consumers, where n is a user-defined variables that can be set by our customers. For example, here, consumer 1 would take queries starting from index 0 up to the size of queries divided by the number of consumers that we have. Then each consumer would then proceed to identify the centroids that we explained in the before slide from the index in parallel and construct an inverted index of the graph centroids needed. For example, this is graph centroid 1, and it's needed by query 1, query 5, and query 6. We then construct n different inverted indices, one for each consumer, and send them to an orchestrator layer in the middle that collects all of these inverted indices and construct a new table which has the consumer and all the graph centroids that it needed. This table is then inverted one last time, which helps us to eliminate repeated IOs. And hence, for example, here we have graph centroid 1 is needed by consumer 1, consumer 2, and consumer n. And all other graphs are, all other centroids are distributed among the keys. Then we divide these graph centroids among our producers, where the size of or the number of the producers is another variable defined by the user. Here, in this case, it's m. And for example, here, graph centroid 1 and graph centroid 2 is sent to producer number 1. Producer number 1 would later fetch, for example, graph centroid 1, and as soon as it's loaded, it will push it in a concurrent queue in all the consumers that needed this data, which is concurrent queue number 1, concurrent queue number 2, and concurrent queue number n. After this stage is done, the search stage starts, and each concurrent queue would then pop the graph centroid and go to the inverted index that we constructed in the previous slide identifies that the graph centroid that was just pushed in the queue and it popped would need a query 1, query 5, and query 6, and then evaluates them. And after this step, you end up with the k nearest neighbor for your consumer. So for our experimental results on the left, you can see how SB tag performs with and without our engine. The blue lines represent SB tag without our engine, and the red lines represent the speed up we gain with our engine. We consistently outperform SB tag. For example, in the MNIST dataset, you can see that we are up to 3 times faster because shorter bars represent shorter time, and hence it's faster execution, which is desirable. And on the right, you can see how we scale as we increase the number of queries and you increase the number of threads that are performing the search. The bottommost line here is the brown line is SB tag with 10 threads in parallel. And using 40% of their computational power, we are able to achieve up to 10x speed up. So for example, this is 650 queries per second. And with our engine, we achieve up to 6,000 queries per second. Here is a demo of our code. On up there, you can see our engine running. It will be done. It's already done in 2.5 seconds, while SB tag would take around 14 seconds for the same number of queries to compute with the same recall. I'll just wait for SB tag to finish. They're pretty slow, but wait for that. Now they finish with the same number of recall, which achieves around 7x speed up. And now Side will continue with our producer-consumer model.
To test out the effect of the number of producers and consumers on our query per second, higher number represent our better results. We ran a couple of experiments with varying number of producers, from 1 producer to 20 producers, and from 1 consumer to 20, with all the combinations between them in this range. And this is what we got, which looks pretty complex, but we're able to break it down into 2 subgraphs, one for the good performance and one for the bad performance. As for the good performance, there are generally 2 cases. When we have low number of producers and any number of consumers, we achieve bad result. This is simply because the disk is not being utilized fully and not producing at its maximum capacity. The second case is when we have any number of producer and very low number of consumers, we achieve bad result. This is because simply the producer thread are oversupplying data more than the consumer thread can handle. While on the good results, for achieving high QPS, we have found that above a certain threshold, the number of producers does not affect the QPS anymore because we have reached the hardware limits of our disk. And now we're going to discuss our second module, which is the filtered search.
Before moving on to explain what filtered search is, let me first explain to you the significance of filtered search. Let's take a look at this snippet taken from Neighbour 21. As you can see, the number 1 recommendation is to support approximate nearest neighbor search queries, which also allow filters such as date, range, and language. And this is exactly what we did. For those of you who don't know, Neighbour is one of the most well-known and prestigious machine learning conferences out there. So moving on to explain what we did, first let me explain to you what filtered search is. Like we mentioned before, we are implementing a document retrieval system utilizing the ANN algorithm, which is typically used with large-scale data sets. This means that a simple search can give a huge number of results. So in order to make our system more efficient in this area, we decided to implement filtered search, in which extra filters are imposed on the query to give more precise results. Filters can be anything from size, area, language, publisher, or anything really. So in order to implement this, we decided to follow this architecture where the filters will be generated manually by the user. When creating a query, he or she will be able to choose the filters they want to apply in that query. Then the text data and the filters will be fed into the embedding unit to give us their vector representation, which will then be fed into the approximate nearest neighbor search algorithm. In our case, it's span, to give us the nearest k neighbors as vectors. Then this will be reverse mapped to return the actual data and the actual results to the user. Now moving on to explain how we added filtered search into the span code. Our first task was to add the filters to each node. We decided to follow this architecture that you see. Each node will hold its data, its actual data and its filtered data. This allows us to easily access the filters whenever we want. The second task we had was to actually use the filters. This was one of the first challenges we met because the distance function used by the span algorithm is no longer valid for us, as does not take the filters into consideration. This is why we had to implement our own distance function called the fusion distance function. As you can see, it takes into consideration the distance between the actual data nodes and the distance between the filters. And it also gives us the ability to manipulate the weights in order to change the weight of each one based on the importance. So for example, if we have a query set where the filters are not that important, we can lower the weight of the filters. Then we had to integrate the fusion distance function into the span code. Of course, this one was one of the most challenging tasks because we decided to integrate it into the 3 stages of span, which are selecting centroids, clustering data, and building the actual graph index. After that, we had to test what we did. So we decided to test the filtered search on generated data in order to make sure that that everything is working as a proof of concept. And then we did tests on real world data to test the validity of our system. And now Mohamed Ayman will talk more about the data sets we use.
Since a filter search in general is on open research a question, and it's somehow new, we needed to have a real data set to evaluate our filter search. And since we didn't or couldn't find any data set, we should have or develop a new data set, which is relying on Amazon US. Amazon US reviews is comprised of nearly more than 12 million data points with more than 8 features. And we have decided to take a subset weight randomly for the training and for the testing. And we needed to select some of the features which are somehow consistent to make sure of the consistency of the data set while evaluating the filter search. And for the generated or for the ground truth, we have tried to use scalable KNN to make sure or to relate it later to calculate the accuracy or the recall of the filter search. And for the results, Sherif will be going through it for the generated and for or according to this developed data set.
Here are the results for the filtered search tests. Previously, we were 3 times slower than SP tag. Here, SP tag is in the red line, and the previous implementation is the blue line. However, we were able, with some optimizations on the distance function, to reach a speed up of about 2 times when compared to the old implementation in the index construction time, and which makes us 1.5 times slower than SP tag. This is mainly due to the fact that the fusion distance functions performs at least 2 distance calculations for every 1 distance calculation performed by SP tag. This is a bigger improvement, especially given the heavy computations performed in the fusion distance function. Secondly, we began modifying the weights depending on our use case and depending whether we want to give more weights to the filter or to the text data. Previously, as mentioned, the fusion distance function provides a mechanism or a weight W, which allows us to modify the weights between the text data and filters. However, when we tested the fusion distance qualitatively on the Amazon reviews dataset, we found that the results retrieved matched the query. However, the text data didn't match at all. This means that the fusion gives more weight to the filters than the text. And also that the graph quality was not the best. So we modified or proposed a new modified fusion distance function that gives proportional weights to the text data and the filter data depending on their dimensions. In more detail, the weight W is now a proportion between the dimension of the data point and the dimension of the data point and filters together. And similarly, a weight is given to the filter distance. However, the dimension of the filters is usually less than the dimension of the data points, so we added a scalar V to the dimension of the filters in order to increase its weight. However, when we tested it, the retrieved results matched more the text than the filters, but we achieved better graph quality. So to balance between the 2 approaches, we divided the scalar V into 2 parts. The first part is when building the index, V is much smaller. And then when we are searching, V is increased to be much bigger than V used in the build stage in order to give more weight to the filters. Here is a quick demo about the filtered search. In the first query, we want a recommendation for a great gift for a child. And we added the filters, the category tools. Here are the first 4 results. The text are similar to the query and the filters match the filters given. In the second query, we want the bad graphics, video games, which are rated 1 star and rated in 2013. Here are the results. As we can see, the reviews match the filters. Also, the text matches the text query. Finally, we wanted to highlight the significance of filtered search. Microsoft just over 3 weeks ago published a paper titled Filtered KNN, which is similar to what we are doing, which shows that the trendiness and the attractiveness of this topic. Now, Fawzi will talk about the embedding part of our project.
For our engine to be utilized, we worked on building a document retrieval system using pre-existing NLP models. In this system, our novelty mainly comes from the deployment of our ANN engine we have developed into a specific use case for news articles retrieval using the multi-news dataset. So the multi-news dataset mainly consists of around 57 news articles in the period between 2012 and 2018, and it also contains summaries. And in the next slide, we can see like that we have designed a pipeline for this specific case. And actually, this pipeline mainly answers two important questions. So the first question is, how could we utilize our ANN engine using this multi-news dataset, especially that neither this dataset nor any other news dataset have queries, and the queries are very essential when it comes to testing and evaluating our system as a whole. So that's one point. And in that case, like we have the documents of the multi-news dataset. We have used a T5 model to generate these queries, like question answer queries. But however, this model has a limitation, which was like it has a certain input. It has a limited size when it comes to the input. So that's why we have this extra step in between, which is a summarization model to get the summaries from these long documents, and then getting these summaries like 512 word articles to be input into this query generator. And once we have the summaries and the queries, they are ready to be input into the embedding module, which you get the embedding vectors for them. And by that, we are using the summaries embedding vectors to build the graph index for the span, while using the embedding vectors for the queries to test and evaluate the model, the system with our extension added to it. So this is the first question. For the second question is, how can we retrieve documents based on users' input queries in real life scenarios? So we have the query from the users that is input to the embedding module, getting the embedding vectors out of it to be buzzed to SB tag to get the nearest neighbor indices, to them be input to a reverse mapping module that will get the documents that are mapped to these summaries indices to be returned to the user. Now coming to the results of this system, Ayman will discuss this.
The first question, we need to take into account which index to use. In other words, as Fawzi highlighted, that we have tried to use the multi-news documents and we have the queries from the T5 model. And then we need to evaluate it over the KNN. But we have tried to use two different ways. The first system design, that we are getting the long documents of the multi-news, which is comprised of more than 3,000 words. And we have the queries, and then we can evaluate it over the KNN. And we have achieved nearly 75% in terms of recall. So we have tried to make into account why is this happening? What if we have tried to use the other way around, which is that we get the summaries and build the index over the summaries and get the queries and then evaluate it over the KNN. And we have achieved a better recall, which is 95%. So we have tried to think about why this happened. For the long documents, as highlighted, that we have more than 3,000 words. So we are trying to use model embedding in general to be in latent space with nearly number of features, 384 or even 768. But for queries as a user, we are trying to get nearly from 60 to 70 words. So adding it into latent space, the misinterpretation will be extremely high. But if we are trying to use the other way around with the queries will be had as percentage or a high percentage of terms in collision, because for each query, we will be having different documents. So we have tried to use the middle way, which is the summaries. So that's why we have achieved better recall. And for the final one, which is the demo. So for example, the first demo is about the President of Fattah Sisi, and we have achieved or retrieved documents related to it. And for example, this is the first document. Okay, so for the distance, for sure that we have tried to be sorted from the first one, second one. And for the second query, we have tried to use, for example, Donald Trump USA election, and we have retrieved, which is similar to the queries that we have tried to do. Thank you.